and thank you for coming and for staying so late for my talk. I'll at least start sort of slowly, hopefully. And I want to talk about a theorem that myself and my three co-authors have been trying to prove for quite a while. And it's an honor to speak with one co-author in the audience. And I can actually wish happy birthday to another co-author, who is absent, but hopefully is having a nice birthday. OK, let's start. So I think the first half of my talk will be introduction. Into cohomology, module categories, and finite generation. And I'll try to say a little bit why I care. So A is going to be finite dimensional Hopf algebra over a field K. And right now, I'm not going to put any restriction on the characteristic, but it will come later on. I come from representation theory. So I'm interested in the category of modules over A, or the category of vector spaces over K on which A acts. And exclusively, in the situations when this category is not semi-simple. We'll see lots of examples of that. It's very interesting. But we still want to study modules and see what we can say about it. So it's not semi-simple. It's a tensor category. Since A is a Hopf algebra, if I have two modules M and N, I can tensor them over the field K, and then A is going to act on them by the coproduct in A. So this actually becomes, we can call it finite tensor category. Okay. And this category is, well, what else does it have? It has enough injectives and enough projectives, so we can do homological algebra in it. In fact, by an old theorem of Larson and Swidler, injectives are projectives. And this actually tells me that I can form a tensor triangulated category out of it called the stable module category. And this is really the category that I want to study. And we'll do it in the following way. So this is a tensor triangulated category. Meaning it has a triangular structure and a tensor structure, and these two structures are compatible. So,
to define the action.
Yes, the action is on the tensor product comes from the coproduct on A. So I'm using that it's a Hopf algebra. Actually, we also have an internal home in this category, which is relevant to it being a finite tensor category, where we use both coproduct and the antipode to define the action on the internal home. So just linear home, and then the Hopf algebra acts on it. OK, so what kind of category is that? For the objects here, I'm just going to define what it is. For the objects, we just take A modules. So it's the same as before. But for the maps, we do the following thing. I'll denote them the underline home between N and M and N. We take the home in the category of A modules, and we factor out the subspace where these are all maps F from M to N, which factor through a projective module. Or, again, because projectives are injectives, they also factor through an injective module. So effectively, what we're doing, we're killing projective modules in this category. Because if you have a projective module and the same projective module, then the identity map factors through that projective module. So effectively, we are saying the identity map is 0, so we just kill all projective objects. So stable module category sort of measures our original category up to projective objects. It has the triangular structure. Triangles actually come from exact sequences of A modules. To give a triangular category, I need triangles and I also need shifts. So shifts are defined in the following way. If you have A module M, you construct an injective envelope or an injective hole, and then you take the co-kernel and call it omega inverse of M. That's the shift in my triangulated category. So this is, like if we think in terms of commutative algebra, there we look at derived categories and they have shifts. Basically, this is the representation theoretic answer to that. That's how we're going to shift modules homologically. Of course, this is not so well defined because I could have taken a different injective module and embed M into it. But I am in the stable module category. So if things differ by an injective object, they're the same. So up to injective object, this is going to be well defined. That's the shift. And then, of course, I have a tensor identity, which is a module K. Right? A is a Hopf algebra. We have an augmentation map, A to K, and this gives an action of A on the trivial module K. And I have a tensor product over K, which is exactly the same as before. Y the coproduct on A, and it's an exact functor, bifunctor, and it's nicely compatible with the triangulated structure. Probably say that, I'm not going to really write it down, but this category, and also the little stable module category, which is exactly the same, except that we only take finite dimensional modules in there. So they're closely related to derived categories and the bounded derived category of A. In fact, if you're algebra geometrically minded, this is the same as the singularity category of A. That's another description of the singularity category. So it sort of measures, this category measures how non-semi-simple your algebra is. The more non-semi-simple it is, the more singular your algebra is, the bigger the category is. And the category is, well, this one is sort of wild and unruly. Where wild is a mathematical term, and unruly is really not. But, I mean, it happens very rarely that you can actually take a Hopf algebra, non-semi-simple Hopf algebra, and classify, say, all indecomposable objects, all indecomposable modules. There are just way too many. And the formal notion for that is wild. So there's no hope to classify them. Say, for a finite group in positive characteristic, you don't really expect to classify indecomposable modules. But we'd like to put some structure on this category, say something about the modules, even though there are way too many. Maybe we can somehow put them into classes, classify something, come up with nice invariants, which would give us some information about what's happening. And this is where cohomology, as one such invariant, comes into play. Although, I realize that there is something else I wanted to say. In this category, we have Hom, and we have graded Hom, because it's a triangulated category. And this is just a direct sum of all the Homs in the category, where we take all the shifts, say, of the second object. This has another name. This is what at least people in group theory call state cohomology. So cohomology comes in. And now I want to look at cohomology of just my Hopf algebra with trivial coefficients. Again, K is a module for A. This is just the X. So here I'm thinking positive degrees of the trivial module with itself. Right? I have this. I can't even forget about the stable module category, even though it's natural to compute it there. I have my Billing category with enough projectives. I can compute derived functors of Hopf. So that's X. This actually is a graded commutative algebra because A is a Hopf algebra. Moreover, it comes with action on my category. And that's basically what we want to do. Like I'm saying that looking at the actions of A on vector spaces is complicated. It's a highly non-commutative object. There are way too many different actions. I'm going to try to replace that with action of this cohomology algebra, which at least is commutative, on something else, just closely related to my original category. And then once I have actions of commutative algebra, I mean, I have all the techniques that people in commutative algebra, algebraic geometry developed to work with. So, in more down-to-earth terms, we have a module M. So A acts on it. Have cohomology ring, AK. And I can also look at cohomology algebra, or cohomology module. So again, M is a module, so there is an X, K, M. And this cohomology acts on that. And there are various ways of thinking about this action. One is Yaneda product. But I'll write down how to think about it explicitly just in terms of composing maps in a minute. Actually, maybe right now. So this is sort of a primitive way of thinking about this. We have A acting on M, that's highly non-commutative. We replace A with this commutative algebra acting on this module, and it still gives me a lot of information about M, and this is what I'm going to study because I can't. I'm sort of simplifying the actions a little bit to get still a lot of information about my original category. More formally, we can have this algebra act on the category, which just means that it acts on the Hopf spaces. You have an algebra acting on the triangulated category, just to have it act on the graded Hopf spaces. Again, I have my cohomology. So this is, well, I can actually rewrite this as Hopf almost. Okay, and looking at all the shifts. So I'm just shifting, let's say, some. Taking X is the same as taking Hopf to the minus nth shift of K. And then I want to act on my graded Hopf, even say n, m, which is a direct sum Hopfs n minus m of m. Well, all I need to do is take one Hopf, another Hopf, and end up in home from n to the shift minus n minus m of n. Okay. That's all my action needs to do. Right? It's an action, a graded vector space. And I can just compose my maps. Trying to show that this action thing is very natural. And this construction works basically in any triangulated category. There's nothing specific about the Hopf algebra. So if I have a map here, let's say phi from k to the shift of k, and a map there from n to the shift of m, what do? Well, first, I have tensor in my category. So I can tensor phi. Oh, actually, let's do it here. I can tensor phi with the identity map on M. But this is just M, 2. And the way shift works, it commutes with the tensor product. So this is just shifting M. And now I can apply this map, but shifted, voila, I get a map from M to the shift of M. So my action is just taking compositions of maps and applying shifts. But in a triangulated category, we often don't even think about applying shifts. They're so natural there. Okay. So that's the goal, to try to study this complicated category via the action of H star AK.
I'm a little bit.
Uh-huh. Yeah?
Your psi goes from n to m, and here you go from n to m. So you should be tensering with n then in the first line.
Oh, did I switch them? Yes. Thank you. Sorry. You're absolutely right. Because one always should go alphabetically. I think at some point I decided I should go alphabetically, but it was too late. Okay, that is okay. No, that's not okay. This is N, this is N, and this is M. Okay, looks better?
Yeah.
Thank you very much. Okay, so I have this algebra acting on big stable module category, also the small stable module category. And then there are various techniques developed to study such actions and what they can tell you about the category. For example, one might hope to, I'm just going to say some words to sort of try to motivate why I want to do it. So one can try to stratify this category via this algebra. In terms of invariance, one can try to construct support theory. Well, that one can just do. One can look at supports of objects just the way we look at supports of modules or sheaves for scheme or commutative algebra. In this category here, that will be an invariant, which remembers quite a bit about your module. In fancy language, one can try to compute what's called the Balmer spectrum of the little stable module category. That's a topological space that, again, gives you quite a bit of information about the structure of the category. Here I'm lying a little bit because the theory that Balmer developed actually was for a symmetric tensor category, but there is a very recent work which does it in the braided settings and considers various like non-commutative spectra, left ideals, right ideals, like whatever people think are the correct notions in non-commutative geometry, trying to apply it in this categorical context. There are a lot of things we can do by acting with this algebra. But if you try doing this, then the first question you're faced with is how nice is this cohomology algebra? And in particular, you'd like it to be of finite type or finitely generated. Okay. So basically, you can't really even start doing reasonable things along those lines until you know that it's a finitely generated algebra. Otherwise, things just don't work well. Okay. There are two conditions to be associated with such an algebra. I'm going to call them finite generation 1 and finite generation 2. And the first one says that it is finitely generated. And the second one actually deals with the modules. It says that if M is a finite dimensional A module, then H star A M is a finite H star A K module. Terminology goes back to a 5-author paper. Let's see. Erdmann, Holloway, Snashel, Solberg, and Teifler, where they actually consider Coxfield cohomology. And if Coxfield cohomology is something you like, you'd probably observe that this would be a more natural thing to take. Well, a reasonable thing to take in terms of actions. You can equally well look at the way Coxfield cohomology would act on that category and study that. For Hopf algebras, there is a way to go back and forth, even though they don't actually give you sort of the same answer if you try to compute these things. But Coxfield cohomology, for example, is more reasonable because you don't have to restrict to Hopf algebra. You can do it for any, like, say, Gornstein algebra or whatever is your favorite, say, finite dimensional algebra. So these 5 people formulated the conjecture in terms of Coxfield cohomology, but we're going to borrow the terminology and ask the question, when is this true? So that's going to be the theme of my talk. We want to know when cohomology is finitely generated as an algebra. The second part is going to be history. So it's still introduction, but some history of the question, which goes back to 1950. And it's a little muddled. But, OK, what is the first Hopf algebra one usually learns about? I guess now it varies, but it probably used to be the case that would be group algebra. So if we take a finite group, well, and let's say here, for the question to even be interesting, we have to assume that we are in the modular setting, namely the characteristic of K divides the order of the group. Then finite generation result was proved back in the 50s and 60s by Gallat, Venkov, 59, and Evans, 61. And the theorem says that FG, I'm going to call these two conditions FG. And in fact, yeah, this is probably the only time when they come separately. It so happens that whenever we can prove FG1, we can prove FG2. But there's also no known formal way of getting FG2 from FG1. So FG holds. But the history is sort of interesting. So Gallat proved it for P groups. Then Venkov proved it for all groups, but he proved it topologically. So it's a beautiful topological proof, but he didn't even worry about modules, and I don't think in his setting it was possible to worry about modules. So he went to classifying spaces and looked what happens there and put everything in the unitary group, and their cohomology is known, explicitly computed. End of the story. Evans independently was working on that. His proof came out later, but he gave an algebraic proof of the same result, which just included, naturally, the second condition about modules. And Evans' name, hopefully, will come up again towards the very end, why his work actually was very important in what we are trying to do. But yeah, for us, algebraic proof is what we want. OK, so finite groups are good. The next thing that came up was restricted Lie algebras. So we're still on characteristic P. And the siblings of these guys already came up, at least in Barbara's talk, the Frobenius-Lustig small quantum groups. I know. I was going to remind people what restricted Lie algebra is. Should I do that? No? Yes, OK. It's quick. So let's say we have an algebraic group. So I already had a finite group. This will be an algebraic group. So it's a fancy G. In characteristic P. So you can think of your favorite one, like GLN, SP2N, whatever, orthogonal group, whatever is your favorite algebraic group. We take its Lie algebra, let's call it G. Then this Lie algebra, define it like any way you want, like left invariant derivations, for example, has an extra structure because we're in characteristic P, the piece power structure. It can be defined axiomatically, but basically it tells you that if you have a left invariant derivation and you take the piece iteration of it, it's a left invariant derivation again. And that's because we're in characteristic P. You're going to take your Newton-Leibniz formula and everything will cancel out. If you're in GLN, that all you're doing is you're taking your matrix to piece power. And this brings you back into your Lie algebra. So it's an internal operation. Because you have this internal operation, you have a finite dimensional Hopf algebra, and this is the sibling of UQ, associated to G, which is, well, we take the universal Veltman algebra. That's a Hopf algebra. It's primitively generated. It's co-commutative, but it's big. And we factor out the ideal generated by this funny thing. Where x to the p is piece power here, the tensor piece power, but this guy is back in G. So effectively, we are cutting everything out at piece powers. If you think about this in terms of PBW basis, then you look at the monomial, and whenever you have in your monomial a power which goes to p or above, you just bring it back down to the first power. So it becomes finite dimensional, in fact, has dimension p to the dimension of G. So it's finite dimensional, co-commutative Hopf algebra. And it was shown by Friedlander, Paschal, and Anderson Jensen back in the 80s that this guy also has finitely generated cohomology. So this satisfies FG. Actually, yeah, I think they proved it in full generality. And then maybe the most celebrated theorem in this subject is due to Friedlander and Sussling from 95. I think I'm not going to write all these long names, but I'm happy to share references afterwards if you're interested. So let's, A is finite dimensional co-commutative Hopf algebra. Then A satisfies FG property. Okay, so cohomology is finitely generated, and the second condition holds as well. One can learn a lot reading this paper. But somehow the main point is that cocommutative allows you to use a lot of geometric methods, because cocommutativity tells you that the dual to this thing is a coordinate algebra of a group scheme. And you work with that group scheme to prove the theorem. And this is what we don't have once we move beyond cocommutative condition. We don't have the geometric methods. OK. I think I'm going to quickly run through various other results, and I'm sure I'll forget. I mean, I can't possibly mention everything, because by now there are lots and lots of results on finite generation, and not all of them about Hopf algebras. There are other things as well, but I'll mention some. Oh, I should say that in that paper, it says, I think I wrote the quote, the paper was published in Vincianis in '95, and there they cautiously say that we don't know if it's reasonable to believe that finite generation holds for any finite dimensional Hopf algebra. But then in 2004, Ettinghoff and Ostrich were much more ambitious, and they actually stated a conjecture in the paper for any finite tensor category, which includes any finite dimensional Hopf algebra. So now it's a conjecture, but it's not clear whose conjecture it is. OK. What else do we know? In '94, Ginsburg and Kummer realized that the methods that Friedlander and Partial used for the restricted Lie algebra can be used for the small quantum groups. And in fact, they actually did more. And should probably mention that there you could do more as well. It's not that they proved finite generation. They calculated cohomology. So they showed that if you take G, say, semi-simple, then you assume that Q, so Q is the root of unity of degree L, and L is bigger than H, where H is a Coxeter number corresponding to whatever is the root system here. Then not only this is finitely generated, it has a very explicit geometric meaning. This is the coordinate algebra of the nullcon of G, where N is the collection of all nilpotent elements in your Lie algebra. Notice how everything quantum disappears from here. In fact, their result was inspired by the result in this setting, where you can also show that the homology of this restricted enveloping algebra, now we are in characteristic P, is this, under the same conditions, except that it's P, which is bigger than H. So cohomology in particular, I was saying how we replace our algebra with cohomology to study actions, but cohomology doesn't see the difference between the restricted enveloping algebra and the small quantum group.
So probably FG is dependent on the condition on the quantum characteristic?
Yes, FG holds, yes. So that's why I stated it. So this is not true for small p and for small l, but FG is always true. And you sort of prove it differently somehow. Oh, sorry, similarly somehow. What happens? I was going to talk about this in a minute. Yeah, I'll say what happens. What else? We'll just say that there are results by Bendel, Nakana, Partial, and Pillen, which remove the condition on L. And then Ian Gordon showed this for the coordinate for the quantum, for the dual of UQ of G, which is an easier algebra, actually. And then together with Masnak, Schoenberg, and Witherspoon, we proved in 2010 a finite generation for certain pointed finite dimensional Hopf algebras with abelian groups of group-like elements. But we had to assume that the orders of these elements were relatively prime with 210. Namely, we had to exclude like 2, 3, 5, 7, 11, which excludes quite a bit of Hopf algebras. So I think Nicholas was denoting this gamma, group of group-like elements. I'm going to denote it gamma. Assume it's abelian.
So knowing FG for a Hopf algebra does not apply to the dual by some formal argument?
Say it again.
If you know FG for a Hopf algebra, you don't automatically know it for the dual?
Very good question. No. That's a very, very good question. It would be nice if you did, but no. But actually, part of our strategy for the theorem that I probably will have time to state is to investigate what happens for the Hopf algebra and for Stringfield double. There is also a very nice calculation due to Stefan and Bay for Fomin-Kirillov algebras, algebra of dimension 12. They also show that cohomology is finitely generated, although just looking up the paper, was it computed? Did you compute? Did you? So it was completely computed, right? That's a very nice, different kind of result. There are other things, like Chris Drupesky proved 3 years ago, finite generation for finite supergroup schemes. So you take Hopf algebras, which are super commutative. And that's actually turned out to be much more complicated than that case. If you add super in there, so you sort of add the simplest braiding possible, and that was already very hard. And he proved it in any characteristic.
He has also some important con behind that, or just
no. This there is no nilpotent con here, right? That's if you just look at this Lie super algebras, then you get something, but that's not, even characteristic 0, that's not known yet. I mean, yeah, that's totally open. Okay. One more comment, historical comment, and I'll stop there. This is very special. Like, for the very first example about finite groups, like you take a finite group, I don't know, GLN, GL5 of F2. You have no idea what cohomology is. Like we know it's finitely generated. We actually know what the cruel dimension is. We know there is a geometric characteristic of that algebra due to Quillen's work in the 70s, but there's nothing like this. We cannot write it as an algebra. We don't know where generators are. We don't know what is the first cohomology which is not 0. So it's like totally up in the air. So this is really, really special that in the Lie theoretic setting, you can actually compute it. And it's generated in degree 2. So I should have said that this n sits in degree 2. Okay. Theorem. So by those 3 people, myself. Oh, I should say that this is a preliminary report. Let's say A is finite dimensional, pointed, Hopf algebra. I already have it here. Okay, pointed finite dimensional Hopf algebra with abelian group of group-like elements over a field of 0 characteristic. Then it satisfies finite generation condition. So, okay. Then, going to make some remarks and also make some remarks about the strategy of the proof. So first of all, the theorem I wrote down before, which we proved like 9 years ago, in that theorem we used extensively the classification by Andrushkevich and Schneider of pointed Hopf algebras, which was available at the time. Since then, there's a lot of progress in classifying pointed Hopf algebras and Nichols algebras. And so one can prove much more. But it also turned out that with all these new Hopf algebras that we know, the old methods, homological methods that we used in that paper didn't work. So we had to change the homological methods as well. And I should have said that all the proofs here I mentioned, and like basically any proof of finite generation, they're very different. There are all sorts of techniques that go in, but there is always a spectral sequence or two or three which go in. So that's a staple of every single proof. And what actually happens in here, why sometimes you prove finite generation, sometimes you prove this, what happens here is that you have the spectral sequence and it vanishes in all odd degrees, which means it collapses. So that's why you have such a nice result. Usually it doesn't happen.
You don't need invariant polynomials, just all polynomials.
No, all of them. You sort of, in a way, already took invariants. Like for the Borel one, you'll get polynomials, and then you take invariants to get n. So one can also write down what happens for the plus, and there you get, honestly, all polynomials on the root vectors. Another special thing about this new case is that, again, before, with these old methods, whenever we would get finite generation, everything was always generated in degree 2. And somehow the methods dictated that. You could only get things generated in degree 2. With what we're doing now, we're actually getting things generated not in degree 2. And cohomology of some of these Hopf algebras are not generated in degree 2, but we can still prove they are finitely generated and actually pinpoint usually the degrees of the generators.
For finite groups?
Oh, no, of course, it's not true finite group, sorry. No. Good point. In the Lie theoretic setting, it often happens. And in that previous theorem for pointed Hopf algebras, we could only prove it for things which somehow happen to be generated in degree 2. OK, quickly, the strategy. There are basically two more or less independent steps. So you have your pointed Hopf algebra, pointed finite dimensional Hopf algebra, and you have, we know that the core radical, which fortunately was already defined for me, is K is going to be C, the group algebra of gamma. Then we have the core radical filtration, which was also defined, which is great. Thank you, Barbara. And then we can take the associated graded. And the associated graded is the Nichols algebra. Oh, sorry, smash product with K gamma. So that's how Nichols algebras come in. I think it's a theorem of many people. Ivan? OK, and Fiona. So we get down to the Nichols algebras. So now we'd like to do two things. So step 1, prove finite generation for Nichols algebras of diagonal type. So that these guys are of diagonal type. Because we're in characteristic 0, taking a smash product with a group, this is semi-simple. It's basically nothing. And 2, we need to do the lifting. So the A is a deformation of this thing. So we know this is finitely generated. We want to go back here. And these are basically two independent things. I should say that basically all the work goes in here. So this is where we use the full force of classification. We need, so what should I say? Right. So we more or less know how Nichols algebras of diagonal type look. They have PBW bases, which are given by generators of our vector V. Since they have PBW bases, so 1. So this actually tells us that we can filter it again and take the associated graded one more time. And now you actually get something really nice. So once you do that, I mean, it's more or less, not more or less, sort of like you take your universal enveloping algebra and take the associated graded. So you get something, you get a skewed symmetric algebra modulo some nilpotent relations which are in the center. So the point is that this is nice enough that one can compute cohomology explicitly. You write down the projective resolution, you compute cohomology, and it's Q symmetric algebra and Q exterior algebra put together. So you know everything you want about this. So you can compute. Then you put it through some sort of spectral sequence machine. And the spectral sequence machine actually has a name. It's called Evans lemma. And this is when we go back to the original proof of Evans for finite group and use the general homological methods that he developed, or philosophy of how finite generation can be proven. Actually, we are still proving things using that. It's just you have to do much, much more. But so you send it through this machine, and you figure out that what you need to do is you need to find enough cohomology classes in here. So basically, by enough cohomology classes, I mean, we explicitly write down cohomology here. We know what generators are, and we match them up with explicit classes we find here. Once we do that, we're good. These guys are called permanent cycles. OK, this is when we get our hands dirty. So we actually write down projective resolution for a trivial module for this Nichols algebra. And we use what's called Annex resolution. So this was a new input in this paper. And somehow Annex resolution seems to work for us. And it's also very nice because it's completely combinatorial. So I'm going to show the picture just for type A2. You can do it in any type. OK, so this Duncan diagram for type A2 is what showed up in Nicholas's talk. That's how you encode your braided vector space. It's two generators. It's three generators. So the Duncan diagram is simply A2. Then you have three root vectors. It's like alpha 1, alpha 2, alpha 1 plus alpha 2. And then you start constructing your resolution. And the resolution, like at every step, like step n, you'll have to write down what chains are. And the chains are going to be paths in this graph. So first, looking at the presentation of your Nichols algebra, you write down the graph. That's not very hard. And it even can be like done algorithmically. Once you have the graph, then a chain of length n is a path of length n in this graph. So for example, a chain of length 2 is going to be x1 times x1 to the n1 minus 1. n1 is the order of q11 of your root of unity. So it's going to be x1 to the n. Or like chain of length 3. So you just go along the graph and you write down your chains. And then the main statement, those permanent cycles or enough classes that you want to write, just powers of root vectors. So in all the situations, we can always say that, so for any root gamma, there is a power such that x gamma, so x gamma is going to be on this first row, to the power L gamma, so that's going to be a path, not necessarily in degree 2, but like, for example, to get x1 to the power 2 and 1, you'll have to go around like 4 times. It's going to be chain of degree 4. OK, then we actually want cocycle, so we'll have to dualize is a cocycle n here. And to show that something is a cocycle, well, you have to show that vanishes on everything. So you have to show that before you dualize, all the boundary maps, all the differentials vanish on that thing. And there you just start computing. And it becomes a very combinatorial question, but this is where we use the full force of classification that Nicholas wrote. Remember, there was these 4 classes. We had the carton type, the super type, the modulo type, and the UFO type. And you go through them, and you prove that this always holds with a lot of difficult calculations. And I was going to show just one UFO thing, since it was mentioned. So this is the thing that will compute the Anyc resolution for one of the exceptional types. But it's still very explicit. Now, do I have till 5 or till 450?
5.
OK, I probably need like 5 more minutes. So that's the first part. One, at some point, write down the resolution and actually shows, case by case, that we have enough elements in cohomology, and that gives finite generation. OK, but then we want to lift it or like deform it. And here one can use clever tricks. So going from B of V smash K, which is the associated graded, to A. Theorem, I think it's also due to Ivan Hiona, saying that the theorem says that we can find a cocycle, sigma, such that if we twist our algebra, the graded algebra with a cocycle, that gives us the lifting, at least up to Morita equivalence of the categories. OK, so Angione and Garcia Iglesias. So there's a very explicit way of lifting. That's really remarkable. Then we also observe that, so this is the Morita equivalence of categories. But now if we have a Morita equivalence of categories like that, then how should I say it? Then we actually get an equivalence of categories between Drinfeld doubles. This tells us that if we can show finite generation in this category, then we have it in this category. So the strategy is to go from, and I'm sort of ignoring the smash product with a group, because again, I'm characteristic 0, it doesn't really matter. We go from GR A to the Drinfeld double, GR A, to the Drinfeld double of A, to A, in terms of proven finite generation. OK, now this is because the categories are equivalent, sort of immediate. This is easy. So going down to prove finite generation is easy. If you have like a bigger algebra and a smaller algebra, and for the bigger one you have finite generation, you go down. This is what was used in the original Venkov's topological proof. He just embedded everything into like a big unitary group, and there he could compute cohomology explicitly. End of story. Going up, or going to a dual, is not at all easy. So we actually managed to do this, hopefully, in a specific case of our Nichols algebras by observing that the Drinfeld double of a Nichols algebra of a given type is going to be, again, a Nichols algebra of the same type. So for the Drinfeld double, we're going back to what we already showed. So we cannot prove this in general, unfortunately. I wouldn't even vouch it's true in general. Well, I guess if you believe that it's true for Hopf algebras. But We don't know any way of doing it generally, but in our Nichols algebra case situation, we can. And the last comment is actually this passage allows one to significantly reduce the number of cases we have to prove in number one, was sort of an added bonus, because in the class of algebras, in the classification, you can look at all the things which are Morita equivalent to have the same Drinfeld doubles and only prove it for one of them, which dramatically cuts down on how many checks you have to do. I think I'll stop here. Thank you.
Questions to the speaker?